Welcome back to QHSE Talks.
Thanks for having me back. I'm really looking forward to this one.
Me too. So if you're listening to this, you are probably right in the thick of prepping for your certification.
Yeah, studying for the ASP exam.
Right. And today we're taking a really close look at ASP 11, Domain 2, Topic 8, Part A.
Which is a mouthful.
It really is. But it's essentially the safety fundamentals of trenching and excavations.
Exactly. And I just want to say right up front, this isn't just about memorizing some OSHA codes to pass a test.
No, not at all.
I mean, it is that, but this specific topic, this is about life and death on a job site.
Yeah, the stakes they're incredibly high.
Because a trench is, well, it's a really deceptive environment.
I want you to picture this. You're standing at the bottom of, say, a 10-foot ditch, right?
Okay.
The air is still. The dirt walls around you look perfectly solid. They almost look like they're made of carved stone.
Right. They look completely safe.
You're just focused on, the pipe you're laying down.
Yep.
Now, imagine a compact car just being dropped on you from the side.
It's out of nowhere.
Instantly, with absolutely zero warning.
Yeah, that's a terrifying thought.
But that is the exact mathematical force of a standard trench cave-in.
It is. And that's the core mission of our QHSE talks today. We want you to master this material so you can actually protect people from that exact scenario.
Right, because opening up the ground, it seems so basic.
Oh, yeah. Digging a hole is like the most primitive task in construction.
You get an excavator, you scoop some dirt, you do the work, and you fill it back in.
It feels completely routine, but from an engineering standpoint, you're creating a temporary wound in the earth.
A wound in the earth. I like that phrasing.
Thanks. And the Earth's natural inclination, millions of years of physics, is to heal that wound by collapsing it immediately.
You're actively defying an ancient equilibrium.
Exactly. So to do it safely, we really have to respect the physical forces.
Okay, let's start with the basics. What exactly are we dealing with from a regulatory standpoint?
Well, the standards are super precise. An excavation is, it's defined as any man-made cut, cavity, trench, or depression in the Earth's surface.
So that's everything.
Yeah. Anything formed by earth removal, a massive skyscraper foundation, or just a shallow fiber optic cable ditch.
But a trench is a specific subcategory of that, right?
Exactly. A trench is typically deeper than it is wide.
Okay.
But the real key metric for the exam is the width at the bottom. It cannot be greater than 15 feet.
So if the bottom is 16 feet wide...
then you're dealing with a general excavation.
Got it. Which has its own rules.
Yeah, but trenches, those narrow, confined spaces, that's where we see the most fatalities.
Because there's just nowhere to run.
Precisely. If a wall fails, the worker is trapped. Which brings us to the main hazard.
The cave-in.
The cave-in. And this goes back to your compact car analogy.
Yeah, let's break down the actual math of that weight.
So a single cubic yard of soil.
Which is, about the size of a standard washing machine?
Yeah, roughly 3 feet by 3 feet by 3 feet. That washing machine-sized cube of dirt weighs a minimum of 2,000 pounds.
Wow.
And if it has high moisture content, it can be closer to 3,000 pounds.
2,000 to 3,000 pounds. That's, the human brain just kind of struggles to comprehend that much weight.
It really does until it's too late. And a trench wall doesn't just, crumble a little bit.
Right. It doesn't just shed a few clods of dirt.
No, it fails along a shear plane.
A shear plane?
Yeah, it's a specific angle where the soil's internal strength just gives up.
Okay, so it detaches as one big piece.
Exactly. A massive, cohesive slab. So you aren't hit by one washing machine. You're hit by a cascading wall of them.
I was reading up on the biomechanics of this. It's actually horrifying.
It is.
Even if the dirt only buries you up to your waist, the compressive force is so immense, it causes compartment syndrome.
Or it crushes your internal organs.
Yeah. And if it hits your chest, even if your face is completely clear and you have eddy...
you can't breathe.
Right. It restricts your diaphragm so tightly you physically cannot draw a breath.
Mechanical asphyxiation. That is the grim reality of a cave-in.
Because you just cannot bench press 3,000 pounds.
No one can. But here is the most fascinating and frustrating part of the data.
What's that?
These accidents are almost never due to a lack of rules.
Really?
Yeah. The regulations exist. The engineering controls exist.
So why is it happening?
In almost every single fatality, known safe work practices were actively violated.
See, that part of the source material made me stop and reread it.
It's a compliance problem, not an ignorance problem.
But if the danger is a suspended car hanging over your head, why take the risk?
It's a psychological trap. It's the normalization of deviance combined with this false sense of security.
Because the dirt looks solid.
Exactly. You dig a trench in heavy clay and the walls look like poured concrete.
You can literally see the teeth marks from the excavator bucket holding perfectly in the side of the wall.
Right. So the crew gets lulled into complacency.
They think, hey, it's been stable for 2 hours, so it's fine.
But the physics don't care. The Earth only looks solid right up until the exact millisecond those shear forces overcome the cohesive bonds.
There's no warning.
None. No structural groaning. No 5-second countdown to sprint away.
Gravity just takes over instantly.
Yeah. You are fighting millions of years of geological settling.
So because human nature is flawed, and people will always want to cut corners to save time,
Right, production pressure is real.
the regulations actually mandate a structural countermeasure.
Yes, but it's not a physical tool, it's a specific human role.
The competent person.
The competent person. This is an absolute cornerstone concept for the ASP exam.
Let's really dissect this, because colloquially, if I say, Bob is a competent guy,
Right, you just mean Bob is good at his job.
yeah, Bob can run the excavator without hitting a water main.
But the OSHA legal designation is vastly different.
Experience is part of it, right?
It's a component, sure, but the strict legal definition has two unbending halves.
Okay, what's the first half?
First, they must be capable of identifying existing and predictable hazards.
Let's pause on predictable,
Sure.
because anybody can spot an existing hazard. Like, oh, look, water is pouring into the hole.
Right, that's obvious.
But a predictable hazard means you need a really deep understanding of cause and effect.
Exactly. It means looking at a dark storm cloud and knowing how that rain will change the soil mechanics in 2 hours.
Or seeing a heavy dump truck idling a block away.
Yes. And calculating how its vibrational frequency is going to travel through the ground.
That's intense. So they have to anticipate the failure before it even happens.
But the second half of the definition is where job sites actually fail compliance.
Okay, hit me.
The competent person must have the authorization to take prompt corrective measures to eliminate the hazards.
Authorization.
Absolute authority.
So if I'm the smartest geologist on the planet, and I spot a crack forming on the trench wall, but I have to call my project manager back at the corporate office to ask for a budget to buy a trench box.
You are not the competent person.
I'm just an advisor.
Exactly. The competent person has the immediate, unquestioned authority to stop work.
They can look at the superintendent and say, shut down the excavators, get everybody out.
We are losing the wall.
Oh.
Yes. If there's administrative friction, the site is legally out of compliance.
That is so critical for safety professionals to understand. Your job is partly to protect that authority.
Because the schedule will always push back.
So what does this competent person actually do all day?
Well, their primary duty is a relentless schedule of inspections.
It's not just a morning checklist.
Oh, no. That is a guaranteed way to fail the exam and get someone killed.
Right.
The standard explicitly states they must inspect the excavation, adjacent areas, and protective systems daily prior to the start of work.
Okay, pre-shift.
And as needed throughout the shift.
Because it's a dynamic environment.
Exactly. Plus, they must inspect specifically after every rainstorm.
Or any hazard-increasing event.
Right.
Like a nearby water main breaking and soaking the ground.
Or a massive crane moving nearby and applying a point load.
So they are constantly reevaluating.
Constantly. But eventually, the physics just surpass standard field assessments.
And this brings us to the magical 20-foot mark.
The 20-foot threshold.
Up to 20 feet, the competent person is the maestro.
They classify the soil, pick the shoring, all of it.
But once that excavator bucket goes down to 20 feet and 1 inch,
The whole regulatory framework shifts. You must bring in a registered professional engineer.
an RPE. Why 20 feet? What changes?
The lateral earth pressures become highly unpredictable.
Because of the sheer mass of the dirt above it.
Yeah, the downward force is so immense that standard charts in the OSHA appendices just aren't sufficient anymore.
Basic aluminum shoring might just snap.
Catastrophically. So an RPE has to custom design the protective system mathematically.
But depth isn't the only thing that summons the RPE, right?
Good catch. No, it's not.
What if I'm digging a shallow trench, like 8 feet deep, but I'm doing it right next to a high-rise building?
That is the other critical trigger. If the excavation might undermine the foundations of an adjacent structure, like a building, a sidewalk, or pavement.
The CP can't just guess if the building will hold.
Absolutely not. An RPE must evaluate it.
Because the building's foundation is basically a massive weight pushing on the side of your trench.
Yes, engineers call it the zone of influence. If your trench cuts into that zone, you've got a massive surcharge load.
So the RPE designs a custom support system to counteract that specific building's weight.
Exactly. It's a really clear division of labor.
The CP handles the daily chaos, and the RPE handles the extreme math.
But both of them base every decision they make on one core variable.
The dirt itself.
Soil classification. This is a
Yeah.
huge part of the ASP exam.
It's life or death in the field. Let's get our hands dirty here.
There are 4 main categories: stable rock, type A, type B, and type C,
Okay, let's start with stable rock,
which is almost a myth in standard construction.
because it's literally solid mineral material.
Yeah, you can dig vertical sides and it stays intact. Think of cutting a channel into solid granite.
So you aren't using a bucket, you're blasting or using heavy breakers.
Right. So for 99% of standard work, we are dealing with actual soils.
Starting with the strongest, type A.
Type A is highly cohesive soil. The defining metric is unconfined compressive strength.
Which means?
It has a compressive strength of 1.5 tons per square foot or greater.
Okay, 1.5 tons per square foot. Let's visualize that.
Think of a 1 foot by 1 foot square of dirt.
Just a tiny square tile.
Now stack 3,000 pounds of weight directly on top of it.
That is immense pressure.
And type A soil has the internal cohesion to withstand that vertical force without buckling sideways.
Because it's heavy clay. The moisture in the clay acts like a microscopic glue binding the particles.
That's a great way to describe cohesion. But the standards are really strict about exceptions.
Meaning it might be clay, but it's not type A.
Right. Even if it tests at 1.5 tons, it cannot be classified as type A if it's fissured.
Meaning it has cracks in it.
Yeah. Or if it's subject to vibration from heavy traffic.
Okay.
Or, and this is a big one, if it has been previously disturbed.
Oh, previously described.
Yeah.
Let's say I'm digging a brand new trench across a field. The clay is gorgeous, dense, type A.
Okay.
But 10 years ago, another crew laid a water line right across my path.
The moment your new trench hits their old trench, the dirt is instantly downgraded.
Because they shattered that natural stratification 10 years ago.
No, exactly. Once you dig it out and backfill it, those microscopic bonds are broken forever.
It never regains its natural tensile strength.
Never. So you drop down to type B soil.
Which is the middle ground.
Right. Cohesive soils with moderate strength. Between 0.5 and 1.5 tons per square foot.
What kind of dirt is that?
Angular gravel, silt loam. Or it could be type A clay that got downgraded because of vibration.
Okay, so it needs significantly more support.
Yes, but then we hit the bottom of the barrel.
The nightmare scenario. Type C soil.
Type C is the most dangerous. Compressive strength is 0.5 tons per square foot or less.
So less than 1,000 pounds.
Yes. And the key characteristic is that it is non-cohesive.
The particles do not bond at all.
Think gravel, dry sand, loamy sand.
It's basically fluid mechanics at that point.
It really is. If you try to dig a vertical wall in dry sand, it just instantly slows down into a pile.
There is zero internal structural integrity.
Precisely. And type C also includes any submerged soil.
Water.
Yes, or soil where water is freely seeping, which introduces the ultimate wild card.
The regulations are absolute about water.
Oh, completely. Employees are strictly prohibited from working in excavations where water has accumulated.
Or is actively accumulating.
Unless adequate precautions are taken, like continuous pumping and specialized shoring.
Let's talk about why water is so destructive.
Yeah.
It's not just that it makes everything muddy.
No, it destroys trenches in 2 very distinct ways. First, it adds a massive amount of weight.
Because water is heavy.
Very heavy. A cubic yard of soil absorbs all that water, and its weight skyrockets, putting insane stress on the trench walls.
And what's the second way?
It acts as a lubricant.
It attacks the shear plane.
Exactly. Remember those microscopic cohesive bonds in the clay?
The glue.
When hydrostatic pressure builds up, the water physically forces itself between those soil particles.
It pushes them apart and lubricates the friction points.
Within hours, sometimes minutes, a perfect type A wall degrades into a collapsing type C nightmare.
So the sloping you meticulously calculated this morning is completely useless by the afternoon.
Because the Earth itself has fundamentally changed states.
That's why the CP has to be so paranoid about the weather and the water table.
It's a living assessment, but, we're focusing a lot on the dirt falling in.
Right.
We can't ignore what might be settling downward into the trench.
The atmospheric hazards.
Yes.
This is a pivot that catches so many people off guard.
Trenches are atmospheric traps.
Right. You look at a trench, you see blue sky above it, you don't think confined space.
But if you understand industrial hygiene, a trench is effectively a basin.
Like a bowl.
Yes. Any gas with a vapor density greater than air, meaning it's heavy, will naturally sink.
And pool at the bottom where the workers are breathing.
Exactly. The standard is very clear. If an excavation is 4 feet or deeper...
4 feet? That's not even chest high on an average person.
Doesn't matter. If it's 4 feet or deeper and a hazardous atmosphere exists or could exist, you must test the air before entry.
What are they testing for, specifically?
First, oxygen deficiency. The air we breathe is 20.9% oxygen.
And OSHA flags it as a hazard if it drops below, 19.5%?
Yes, exactly. But oxygen doesn't just disappear, it gets displaced.
By those heavy sinking gases.
Carbon monoxide is huge.
Jacopo.
Yeah. If you have an idling excavator or a gas generator or a concrete saw near the lip of the trench...
That dense exhaust just rolls right over the edge.
And sinks to the floor, silently suffocating the crew.
Then you have hydrogen sulfide, H2S.
A massive risk in municipal utility work.
Sewers, decomposing organic matter.
Right. And H2S is terrifying because it's deceptive.
It smells like rotten eggs at first, right?
Initially, yes. But it rapidly deadens your olfactory nerves.
So you smell it, then the smell goes away.
And the worker thinks, oh, the wind blew it away, we're safe.
But really, their nose just stopped working, and the gas is about to kill them.
It's incredibly lethal. And then we have explosive atmospheres.
Primarily methane, right?
Yes. The methane pooling in a trench. If it reaches its lower explosive limit, the LEL...
Just one spark from an excavator bucket hitting a rock.
Or a worker lighting a cigarette.
It causes a flash fire inside the trench walls.
A catastrophic explosion in a confined space.
And speaking of methane, the exam blueprints have a specific call-out for landfill excavations.
Landfills are uniquely hostile.
Because it's not just soil anymore.
No, you're cutting into a massive, uncontrolled chemical reactor.
All that decomposing garbage.
It continuously generates vast quantities of methane, H2S, and VOCs.
Volatile organic compounds.
The risks there are extreme. Engulfment by unstable trash, rapid asphyxiation, severe fires.
So atmospheric monitoring has to be continuous?
Non-negotiable.
So the CP is playing three-dimensional chess.
That's a good way to put it.
Calculating the weight of the walls falling in, monitoring the water rising up, and testing for gases sinking down.
All at once.
Which brings us to the core geometry of the job site, the rule of numbers.
This is critical. You have to memorize these thresholds for the ASP exam.
2 feet, 4 feet, 5 feet, and 6 feet.
Let's start at the surface, the 2-foot rule.
Okay, what happens at 2 feet?
2 feet is the mandatory minimum setback for all surcharge loads.
Surcharge loads, that means the spoil pile, right?
The excavated dirt, yes, but also heavy equipment, pipe joints, construction materials.
Anything heavy.
It must be kept at least 2 feet away from the leading edge of the trench.
We have to explain the physics here, connecting back to the 2,000-pound washing machine.
Let's do it.
If I pile 10 cubic yards of wet soil right on the lip of the trench.
You've added 20,000 pounds of vertical pressure right above the unsupported wall.
But that vertical pressure doesn't just go straight down into the center of the earth.
No, in soil mechanics, vertical pressure translates into lateral pressure.
It creates a diagonal shear force pushing outward against the trench wall.
Which dramatically increases the chance of a blowout.
So pushing that weight back by 2 feet
distributes the downward force away from the shear face, putting it over a supported column of earth.
Geometry and force distribution. Okay, moving down. The 4-foot rule.
We already mentioned 4 feet triggers atmospheric testing.
Right.
But 4 feet is also the depth where safe access and egress become legally mandatory.
Ladders, stairs, ramps.
Yes. And there is a very strict spatial requirement.
The 25-foot rule.
Egress must be located so as to require no more than 25 feet of lateral travel for any worker.
Let's really look at this, because if I'm a contractor, I might think, why do I need so many ladders? I can just walk 50 feet down the trench to the ramp.
Connect it back to the reality of a cave-in.
It's instantaneous.
You might hear a crack or see a trickle of sand, and the wall is already coming down. You have maybe 1 or 2 seconds.
Right. And if the ladder is 50 feet away, trying to sprint that in a muddy trench, wearing heavy steel-toed boots, stepping around pipes.
It's physically impossible. You cannot outrun a collapsing wall over a 50-foot distance.
25 feet gives you a fighting chance to drop your tools, pivot, and die for the ladder.
Exactly. And the ladder itself has rules.
It has to extend at least 3 feet above the landing surface.
Yes.
Which is basic biomechanics. When you climb out, your center of gravity shifts backward as you step over the lip.
If the ladder stops flush with the ground, you have nothing to hold on to.
You'll just fall backward right into the trench.
That 3-foot extension gives you the handhold to pull your center of gravity forward.
And what about step ladders?
Absolutely forbidden.
You can't just pop open an A-frame at the bottom.
No. It must be a proper straight or extension ladder, set at the right angle, and secured.
Okay, so that's 2 feet and 4 feet. Now, the most famous number, 5 feet.
5 feet is the depth at which engineered cave-in protective systems become absolutely required by law.
Unless you're in stable rock.
Right, but we established that's rare. So at 5 feet, you must slope, bench, shore, or shield.
No exceptions for convenience.
None.
But this is where the exam sets a trap. Let's look at the inverse of the rule.
Oh, this gets so many people.
A contractor digs a 3.5-foot trench for a residential utility line.
And they think, awesome, I'm under 5 feet, I'm legally in the clear, no shoring needed. That is a massive misconception.
The numbers are legal minimums, not magical force fields.
Exactly. The regulations explicitly state that for trenches less than 5 feet deep, a protective system is still required if the competent person sees any indication of a potential cave-in hazard.
If that 3-foot trench is wet, sloughing type C sand,
a collapse is imminent.
And getting hit in the knee with 1,000 pounds of dirt will shatter your leg.
The CP has the authority to mandate shoring at 3 feet if the physics demand it.
So 5 feet is where debate ends. Under 5 feet, the hazard assessment dictates the action.
Perfect summary.
And briefly, the 6-foot rule.
At 6 feet, we pivot to fall protection for people outside the hole.
Walkways or bridges crossing over the trench need standard guardrails once the drop hits 6 feet.
Comprehensive hazard management.
Okay, so once we cross that 5-foot mark, we have to manipulate the environment. We have 4 main defenses: sloping, benching, shoring, and shielding.
Let's start with sloping and benching, which alter the shape of the hole.
Removing the hazard by changing the geometry. Sloping cuts the walls back to the angle of repose.
Which is a beautiful concept.
Think about pouring dry sugar onto a table. It forms a natural cone.
The angle of those sides is the angle of repose.
If you try to make it steeper, gravity overcomes friction and the sugar slides down until it stabilizes.
You do the exact same thing with the earth, but the angle depends entirely on the soil type.
Let's do the math. Type A soil, very cohesive.
The standard maximum allowable slope is 34:1.
So for every 1 foot of depth, you cut back 34 of a foot horizontally.
It's a relatively steep V shape.
But as we lose strength, the angle flattens. What about type C?
Type C, practically no cohesion, requires a slope of 1.5:1.
1.5 feet outward for every foot down. Let's apply that to a real project.
Okay, say you have a 10-foot deep trench in type C soil.
You have to slope the walls back 15 feet horizontally on each side.
Yes, measured from the top edge of the vertical cut.
So if the bottom is 5 feet wide, plus 15 feet of slope on the left, plus 15 feet on the right.
Your trench is now 35 feet wide at the surface.
You started digging a pipe trench and you ended up with a crater.
Exactly. Sloping has a massive spatial footprint.
What about benching?
Benching achieves the same angle of repose, but you cut the walls into horizontal steps or terraces.
Like a staircase.
Yes. But there's a huge caveat you must remember. You cannot bench type C soil.
Because it's non-cohesive. You try to carve a step into wet sand, it just crumbles.
Precisely. So sloping and benching are great out in an empty field. Space is free.
But what if you were laying a water main down the center of downtown Chicago?
You don't have 35 feet of space.
You'd rip up both lanes of traffic, sidewalks, and undermine a skyscraper foundation.
Space is money in an urban environment.
So you have to use vertical systems, like shoring.
Shoring is an active system.
Meaning it applies counterpressure.
Right. You install a framework, usually aluminum hydraulic cylinders, that actively pushes outward against the trench walls.
As the soil tries to push in, the hydraulics push out with equal or greater force.
It locks the soil structure in place, artificially.
And you can install it from the surface, right?
That's a huge safety advancement. Drop the rails in, hook up a pump, pressurize it. No one enters until the walls are supported.
Active pressure.
Right.
But what if you just want a solid barrier?
Then you use shielding, trench boxes.
We need to make this distinction crystal clear.
It's constantly misunderstood.
Shoring actively prevents a cave-in.
A trench box does not prevent a cave-in.
It's passive. I love the shark cage analogy.
It's perfect. A shark cage doesn't stop the shark from attacking.
It just sits there. And when the shark bites, the heavy steel bars protect the diver inside.
A trench box functions exactly the same way. The earth can and does collapse around it.
But the workers inside are safe from the crushing force.
Because it's passive, relying purely on its structural integrity, the rules for using it are incredibly strict.
You have to stay entirely inside the geometry of the box.
If you lean your head out the end to connect a pipe...
You just stepped outside the shark cage.
Right. And there's a highly tested rule about vertical placement.
Ideally, the box sits perfectly flush on the bottom of the trench.
But the regulations allow for a slight gap, so you can actually fit the pipe underneath.
The 2-foot rule again. The bottom of the box can be no more than 2 feet above the trench floor.
But, and this is a massive but, you can only utilize that 2-foot gap under very specific conditions.
The shield has to be designed and rated for the full depth of the trench.
And, crucially, there can be absolutely no sign of soil loss from behind or below the system.
Imagine wet type C sand. If you leave a 2-foot gap at the bottom,
the massive vertical pressure of the earth behind the box will force that wet sand to flow right under the edge.
Like toothpaste being squeezed out.
Yes, it squirts out into the trench floor.
And the void left behind the box destabilizes the entire wall.
The heavy trench box itself can shift, bind up, or just drop.
So if the CP sees any dirt sloughing into the edge, that 2-foot privilege is gone.
Instantly revoked. You must dig it down flush.
So we use these vertical systems in urban environments. But digging in a city introduces a whole new matrix of nightmares.
A trench doesn't exist in a vacuum.
We have to look above and beneath the hole. Surface encumbrances and underground utilities.
Let's start below. Trenching in a city is like open-heart surgery on infrastructure.
You have water, electric, gas, communication lines everywhere.
And hitting one isn't a minor penalty. It's apocalyptic.
An excavator bucket catches a high-voltage line.
Immediate, lethal electrocution.
Fracturing a high-pressure gas main.
Massive explosive atmosphere.
Rupturing a water main.
The trench fills instantly, workers drown, the soil liquefies, and the walls immediately cave in.
Because of that, you can't just dig and hope for the best.
No. Estimated locations of all underground utilities must be determined prior to opening an excavation.
You have to call 811 or the local equivalent.
Advise them of the work and let them mark the earth with paint and flags.
But the standard address is reality, too. What if the utility company is unresponsive? If they just never show up, can the contractor fire up the excavator and say, well, I tried?
Absolutely not. The protocol is very specific.
If they don't respond within 24 hours or can't find the lines,
the employer can proceed, but only with extreme caution.
Using acceptable non-destructive means to locate the utilities.
You can't use a heavy steel bucket.
Hand digging with shovels or hydro excavation.
Yes, using high-pressure water and a vacuum to melt the dirt away safely.
And once it's exposed, you have to protect it. Say you dig a 10-foot wide trench and you expose an old cast iron water main running straight across it.
You successfully dug around it.
But now you have 10 feet of heavy, water-filled cast iron suspended in midair.
Unsupported by the earth.
If the sheer weight of that pipe snaps the joints,
your trench floods. You must engineer a sling or structural support to carry that weight.
It's constant engineering foresight, which applies to the surface too.
Surface encumbrances, trees, boulders, telephone poles.
If you're digging near a massive oak tree, the CP has to assess the roots.
Did we sever the taproot? Is the weight of that tree going to act as a surcharge load and pull the wall down?
If so, the tree has to go.
And the most dynamic surface encumbrance. Heavy machinery.
Dump trucks backing up to the edge of the hole.
Staggering rear axle weight.
If those back tires get too close to the shear plane, the wall blows out and the truck rolls backward onto the crew.
To prevent that, you have to use physical barriers.
Staff logs, barricades, earthen berms.
Physically preventing the tires from rolling over the critical edge.
Especially if the operator's view is obstructed.
It all comes back to anticipation.
Anticipating failure points in the dirt, the water, the air, the utilities, the machinery.
Before they happen. That is the essence of ASP 11, Domain 2, Topic 8, Part A.
Let's pull all of this together. Our mission today on this QHSE Talks was to understand the brutal realities of trenching.
Yes.
Protecting workers from that immense 3,000-pound crushing force requires uncompromising vigilance.
Relying entirely on the competent person to wield their authority.
Accurately diagnosing microscopic soil cohesion. respecting the 4-foot egress rule, the 5-foot mandatory protection threshold.
And mathematically choosing the right engineering controls.
Whether that's a massive sloping footprint or a passive trench shield.
We've covered a lot of technical specs today, but I want to leave our listeners with a broader challenge.
Okay, let's hear it.
We walk across the earth every day. We build homes on it, pave roads over it. So we inherently view the ground as this permanent, static, unmovable foundation.
It feels incredibly safe.
But it's not static. It's a complex system of pressures, friction, moisture, and gravity, all locked in a delicate geological stasis.
And the moment you bring an excavator in and break that surface,
You are violently disturbing an ancient equilibrium. The earth immediately attempts to close that wound.
wow.
So as a safety professional, you have to reframe your perspective.
Yeah.
You aren't just memorizing OSHA codes to pass a multiple choice test.
You are actively managing the fundamental laws of physics.
Your job is to calculate the forces of nature, deploy engineered countermeasures, and guarantee that the people who dig into the earth to build our world are never buried by it.
That is so powerful.
So I ask you, having explored the mechanics of a cave-in, the deception of a solid wall, and the sheer weight of a cubic yard of soil, how will this knowledge change the way you evaluate the very next construction site you walk past?
It is a profound perspective. You aren't just a compliance officer checking a box.
No.
You are the last line of defense holding back gravity.
Well said.
Thank you so much for joining us on this QHSE Talks.
It was my pleasure.
For everyone listening, take this knowledge. Respect the physical forces at play, apply it to ace your AST exam, and most importantly, use it to ensure your people always make it out of the trench alive. Until next time.